Hello, I'm Han, and I'm glad to share our work with you, PersPose 3D human pose estimation with perspective encoding and perspective rotation. In this work, we focus on 3D human pose estimation, which aims to predict the 3D positions of human joints from individual images, and it has a wide real-world uses such as AR, VR, and human-computer interaction. As for existing methods, most 3D HPE approaches only use cropped images as input. However, the relative depth of joints cannot be accurately estimated from cropped images without the corresponding camera intrinsics, which determine the perspective relationship between 3D objects and the cropped images. We use two examples to show the importance of camera intrinsics in 3D HPE. Case 1 shows a camera capturing 3 human subjects with identical body shapes. The resulting images and the cropped images are also shown in the figure. The blue lines denote the relative depth from the left hand to the pelvis, while the red lines represent the arm length. In addition, the red lines for A and C are parallel. From the cropped images, we can see that first, although human subjects A and B have different relative depths, they yield the same cropped images. Second, subjects A and C share the same relative depths but produce distinct cropped images. So from cropped images alone, it's hard to accurately estimate the relative depths of joints. Case 2 shows that even when using the full image but without FOV information, the estimation of joints' relative depths is still inaccurate. In this case, two cameras at a varying distance from a human subject capture images, resulting in images A and B. Both cameras share the same optical axis but different FOVs. The two images look quite different, but they have the same relative depth labels. This shows that FOV is also important for depth estimation. On the other hand, cropping an image is equivalent to capturing a photo using another camera with the same camera extrinsic but with different camera intrinsics and resolution. The cropping operation includes scaling and translation, which is equivalent to adjust the focal length f and modifying the coordinates of the principal point cxcy as implemented in this equation. The camera intrinsics corresponding to the cropped image, which we call cropped intrinsics, effectively encapsulate both the cropping and the FOV information. In this work, we propose a new 3D HPE framework. First, considering the importance of camera intrinsics, we introduce perspective encoding PE to encode the cropped intrinsics, including the focal length and the principal point coordinates as a 2D map. This map is then fed into the neural network together with the cropped image. In this way, the network learns to map the cropped image I crop, the focal length f crop, and the principal point coordinates cxcy to 3D joint positions pxyz. However, considering that the human subject can appear anywhere within the original image, the principal point of the cropped image may vary a lot. This makes the model hard to fit. On the other hand, the further the human is from the image center, the greater the perspective distortion becomes. To address these issues, we propose perspective rotation PR to center the human, so the mapping can go from this to this as the principal point becomes consistent across different images. Regarding the detailed implementation, To efficiently encode cropped intrinsics, PE projects virtual sensors onto a fixed reference plane and uses the corresponding projected area as the encoding result. For example, there are three virtual sensors with different cropped intrinsics. The red virtual sensor has a larger focal length compared to the green and blue virtual sensors. Additionally, the red and green virtual sensors are aligned along the optical axis, while the blue virtual sensor is placed off-axis, which is common for cropped images. For their projected areas, the red virtual sensor has a larger focal length than the other two virtual sensors, so its corresponding projected region is smaller. Similarly, the principal point of the blue virtual sensor deviates from the optical axis, and its corresponding projected region also shifts away. Overall, for each sensor, the corresponding projected area geometrically represents its unique view frustum determined by their cropped intrinsics. So we use this projected area as the encoded representation of the cropped intrinsics. Through PR, the original image I is transformed into the image I prime to center the human subject. Here is an illustration of how this is done. In Figure A, a virtual sensor captures an image I with the human bounding box center marked as UCYC. An upscaled image U is added to the scene on the plane at z=1, and the human bounding box center XCYC1 on U is also marked. A 3D human skeleton PXYZ is also added to the scene. The virtual sensor, the upscaled image U, and the 3D skeleton PXYZ conform to perspective relationship. It means if a ray is projected from a particular joint of PXYZ toward the optical center O, the ray passes through the corresponding joint in the original image I on the sensor, and also through the corresponding joint in the upscaled image U. Next, rotate the 3D skeleton PXYZ and the upscaled image U around the optical center O from A to B, so that the optical axis points to the human subject. After this rotation, the upscaled image U prime in B is reprojected onto the virtual sensor in B, and the centered image I prime is obtained. So here is the overall framework of our PersPose. First, PR transforms the original image so that the human is located in the center. Then, the centered image is cropped. After that, PE encodes the cropped intrinsics into a 2D map. This PE map MXY and the cropped image iCrop are processed separately through different convolution layers and then added together element-wise. The fused features are passed through a backbone network, and a decoder predicts the 2D joint coordinates and the relative depths of joints PUVD, as well as a scale factor as height. These outputs are used to compute the rotated 3D pose P', which corresponds to centered image. Finally, the inverse rotation is applied to get the 3D pose for the original image. We evaluate the performance of the proposed PersPose on several datasets. To compare with the HPS methods, we additionally add two linear layers into the PersPose decoder to estimate human shape and twist, and the analytical IK algorithm in HybridIK is used to derive SMPL parameters prediction. We use this matrix to evaluate the precision of joint positions and mesh vertex positions. The table shows that PersPose achieves SOTA performance on several datasets. To evaluate the effectiveness of our PE and PR modules, we conduct ablation studies comprising the following configurations. 1. Our framework without PE and PR. 2. Our framework without PR. And 3. Our framework with both PE and PR. This table displays that the addition of PE or PR consistently leads to performance improvements across both datasets. On MPI-NF3D-HP dataset, the addition of PE or PR results in a considerable reduction in depth error. On 3D-PW dataset, incorporating PE or PR leads to a relatively modest performance improvement compared to MPI-NF3D-HP dataset. To investigate this effect, we display the distribution of the rotation angle phi in PR across different datasets in this figure. The rotation angle phi for MPI-NF3D-HP spans a broader range than 3D-PW. This distribution quantifies the variability in the person's position within the dataset's images. A wider spread in phi indicates greater variation in the center of the Hillman bounding box (UCVC), reflecting significant changes in the perspective relationship between the 3D scene and the cropped image. In such cases, the benefits of PE and PR become even more pronounced. Finally, here are some visualizations. The first and second lines show that with PR, perspective distortions are reduced. The last two lines show some HPE and HPS results. Thank you for listening. Bye-bye.